Hello, I'm Professor Bob Brown, and today we're going to talk about a way of solving logic problems. I'll bet you didn't know that you can do math on true and false, but you can, and you can use that to solve interesting and otherwise maybe knotty problems. What kind of problems? Well, redstone projects in Minecraft for one, and if statements when coding for another. We'll talk about more uses after we've seen how this works. Right now, I want to introduce my friend Kat, short for Catherine. Kat has just gotten her Hogwarts acceptance letter and she's very excited. The letter says students may bring an owl or a cat or a toad. Kat has never heard of a girl having a toad for a pet and she thinks an owl might be a lot of trouble. So Kat needs a cat. But what kind? Well, Kat will take any cat as long as it's black. She's a witch, right? She's going to Hogwarts. What if there are no black cats? Kat will take a female cat if it's neutered because she doesn't want kittens while she's at school, and either white or orange. And if there are none of those, well, a male cat neutered in any color but white. This is a problem that we can solve with the mathematics of true and false, but first we have to introduce someone else. This guy who looks like his teeth hurt is George Boole. Boole was a British mathematician and philosopher of the 19th century. He made a number of contributions to mathematics. An important one, and the one that's interesting to us today, is the Boolean algebra. That's an algebra over finite sets of discrete values. Man, a couple of big words. Finite means I can list all the values in a set, and discrete means that the variables have distinct values like true and false, or the counting numbers, rather than continuous values like real numbers. Let's introduce the concept of a Boolean function, and we'll start with the AND function. Boolean functions are those in which the variables are either true or false, no other possibilities, and the result is either true or false. Consider A dot B, where that center dot represents AND, and remember the variables A and B can only be true or false. A and B is true if and only if A is true and B is also true. For all other combinations, A and B is false. This is the AND function, or the Boolean product. That was a little bit complicated. There is a more visual way to represent Boolean functions, and that way was developed from the work of C.S. Peirce and Jan Łukasiewicz. That's Professor Łukasiewicz there in the picture, and he looks a little bit like my grandfather. So let's take a Boolean expression. I had fruit and cereal for breakfast, and we'll make that expression into a truth table. Our two variables are fruit and cereal, so we're going to have a column for fruit and another column for cereal. We're going to fill in all possible values. There are going to be 4 rows because there are 4 combinations of true and false. Let's look. If fruit is false and cereal is false, that's one combination. Fruit's false and cereal is true, that's another one. Fruit's true but cereal is false, that's another one. And the last possibility is that fruit and cereal are both true. Now, let's look at the result. The result is going to be fruit and cereal. If fruit's false and cereal is false, the result is false. If fruit's false and cereal is true, the result is false. If fruit's true, cereal's false, the result is still false. The result is true only when both fruit is true and cereal is true. That's the AND function. Let's look at another one. The OR function is represented by plus, and I'm going to tell you twice that that's not the same as the arithmetic plus. We're going to read it as OR. A or B is true when either A or B or both of them are true. So let's think of another Boolean expression. Cake or ice cream will make me happy. and we'll write the truth table. It's going to have 4 rows just like the previous one, and we're going to write them in the same order. We always start with false, false, then false, true, true, false, and finally true, true. So let's see what it takes to make me happy. There's the result. If I have no cake and no ice cream, I'm not happy. If I have no cake but I do have ice cream, I'm happy. If I have cake but no ice cream, I'm happy. And if I have both cake and ice cream, I'm still happy. I can't be twice as happy because my only values are false or true, and in this case it's true. The OR function is inclusive, either one of them or both of them. And now, for the second time, let me say it's not the same as the arithmetic addition operator, plus. The NOT function is a little different. There's only one variable, and the result is the opposite. We indicate the NOT function with an overbar over the variable. So another Boolean expression, any vegetable but not zucchini will make me happy. Our truth table is only going to have 2 rows because zucchini is either true or false. So let's look at it. If zucchini is false, happy's true. If zucchini is true, happy is false. Let's get back to our problem. Cat needs a cat, any cat as long as it's black, or a female cat neutered in white or orange, or a male cat also neutered in any color except white. Our variables need to be either true or false. We can use male as a variable and neutered as another one. If we use male as a variable, how do we represent female? That's exactly right. Female is not male. Now we have to think about color. And Cat named 3 colors, black, white, and orange. But for that male cat, she also said any color but white. For that other color, we really only need not white, so we don't need to add another variable. Let's do one of the choices. Female neutered in either white or orange. We've already said that we can represent female as not male. Neutered gets connected with an and, that center dot is and, so not male and neutered and white or orange. But now we have a problem. Does or come before and? In fact, it turns out that and takes precedence, but we can use parentheses to get what we need. And now we have the complete expression, not male and neutered and parenthesis white or orange unparenthesis. Now, if you're viewing this video in a classroom, the teacher's going to pause the video for a few minutes while you do some work. Let's write the Boolean expressions for all 3 of Cat's choices. Any cat as long as it's black, female, neutered, and white or orange, or male, neutered in any color except white. We're back from our pause. The first expression is really easy. It's just black. The next one is not male and neutered and parenthesis white or orange. That's the one we did just a moment ago. And the third one is male and neutered and not white. We're not done though. We have to combine those 3 so that we get an expression that will represent any cat that cat might want. We combine them with ors because Cat will take any one of those cats. And there they are. Black or, and we need some parentheses, not male and neutered, and parenthesis white or orange, or, more parenthesis, male and neutered and not white. That's Cat's ideal cat. Now, I have to confuse things by telling you that and, or, and not are concepts, and the notation is different depending on the context, that is, on how these concepts are used. The notation that we've used here is the notation of computer science. with the center dot meaning and, the plus sign meaning or, and the overbar meaning not. In classical logic, we use an upward pointing symbol to mean and you remember that because it looks like the A in and. Invert the symbol to mean or, and we use a hook to mean not. In programming for Java, the double ampersand represents and, the double vertical bar represents or, and the exclamation point represents not. In Python, we use the words and, or, and not directly. In programming, you'll often see 1 for true and 0 for false. Don't let this table make your brain slam shut. The important thing to remember about this table is that it exists. If you remember that it exists, then you can find a copy of it when you need it. The table introduces something that we've used before but haven't really defined, and that is the equal sign for same as. And each one of these rules of algebra, they're called identities, has two forms, an and form and an or form. Let's look at the and form of the identity law. True and A is always equal to A. Think about it for a minute. If A is true, true and true is equal to true. If A is false, true and false is equal to false. And in either case, true and A is always equal to A. So we change the true to false in the or form. False or A is always equal to A. Let's look at another one, the distributive law, because we're going to use that in a minute. And we're interested in the or form. So let's look only at the or form of the distributive law. A and parenthesis B or C is the same as A and B or A and C. Now, an important thing about this table is you'll often see it in the context of programming, and when you see it in a programming book, it's likely that there are ones where I have trues and zeros where I have falses. So when you see the table in a book, it's quite likely to look like this. Don't worry about it. It means the same thing. You can think of 0 as none and 1 as some, but it tells you some, but not how many. Now, in our expression, both of the last two terms contain the variable neutered. We can factor it out by using the distributive law, and the easiest way to see that is to just do it. So let's do it. We say black or neutered has been factored out onto a line by itself. We had to add some more parentheses, so neutered and not male and white or orange, or male and not white. Simplification can make coding easier. So you're going to use simplification when you are programming to make your programming statements easier to understand. And if they're easier to understand, they're easier to write correctly. One other thing about programming, the last thing in that table was De Morgan's law. De Morgan's law is your friend when you're coding and you have to mix and, or, and not. The and form says not A and B, the not bar is over both of them, is the same as not A or not B. Moving to the or form, not A or B, the overbar over both of them, is the same as not A and not B. The way you remember this is break the line, change the sign. If we were writing in Java, we would say that not parenthesis A and B is the same as not A or not B. That's the and form. We'd also say that not parenthesis A or B is the same as not A and not B. So at the beginning, I promised we'd talk about what this is good for, and one of the things that I mentioned was redstone projects in Minecraft. If you do Minecraft, Redstone is all about Boolean logic, all about true and false or on and off. And if you write down the expression that you want to build in your Redstone project, you're going to get it right. We can use this approach for working through complex logical problems, for untangling logic in programming and coding, especially if we can simplify things. Now, I have another retired college teacher friend, and he emails me jokes. And they're funny jokes, but sometimes I'm busy and I don't particularly want to read his joke right when it arrives. So I write email filters that put my friend's jokes into a folder, and I can go look at them when I am ready. Those email filters are Boolean expressions. I can design digital logic circuits, which some of you may do. That might surprise you to think that you're going to do that, but you might. And there are many other things to which we can apply the logic of true and false. Let's do one last exercise. A logician goes into a restaurant and says, I want a hamburger or a hot dog and French fries. We learned a few minutes ago that and has precedence over or, and we know that the English or is exclusive. That means we choose one or the other, but we probably don't get both. So, which of the following is correct? Just a hamburger, just a hot dog, just French fries, a hot dog and fries, a hamburger and fries, a hot dog and a burger, all three, or because he's a smart aleck, the logician gets nothing at all. Now, if you're in a class, the teacher's going to pause the video for a few minutes and let you solve that problem. And has precedence over or is exclusive. Which of those things does the logician get? Like cats, there might be more than one correct answer. We're back from our pause, and I know that logician, and he's a little mixed up. Suppose the precedents were reversed and or had precedence over and. That is, we do the ors first, then the ands. What would the answer be in that case? Time for another pause. We're back from our pause. If and has precedence, that's the first one, we'd put our parentheses around the part of the phrase that has an and in it, a hamburger or a hot dog and French fries. And if we look at our answers, the logician would get just a hamburger or he'd get a hot dog and French fries. Now, what our logician probably really wanted was some kind of mystery meat and some potatoes that were fried in grease. So he probably meant or to have precedence. And in that case, we'd put the parentheses around the or part of the phrase, a hamburger or a hot dog and French fries. In that case, our logician wants a hot dog and French fries or a hamburger and French fries. Those parentheses are your friend. That's everything I have to say about Cat's Cat Checker. I had fun making this video, and I hope you had fun watching it and maybe learned something that will help you.